Today we're going to explore one of the most beautiful stories in physics, how the mysterious spectral lines of hydrogen led to our understanding of atomic structure. In the 19th century, scientists discovered something puzzling. When you heat hydrogen gas or pass electricity through it, it glows with a distinctive color. When you pass this light through a prism or diffraction grating, instead of seeing a continuous rainbow of colors, you see only specific, discrete lines at certain wavelengths. The visible spectrum shows four prominent lines: a red line at 656 nanometers, a cyan line at 486 nanometers, a blue line at 434 nanometers, and a violet line at 410 nanometers. This raises a fundamental question. Why does hydrogen emit light at only these specific wavelengths and not at others? Scientists in the 1800s measured these wavelengths with increasing precision. They found additional lines in the ultraviolet and infrared regions as well. Here's a table showing some of the measured wavelengths. The visible lines are called H-alpha, H-beta, H-gamma, and H-delta. There are also lines in the ultraviolet and infrared. The first natural approach was to try fitting these wavelengths with a simple polynomial. Maybe the wavelengths follow a pattern like a plus b times n plus c times n squared, where n is just 1, 2, 3, 4. Lambda equals a plus bn plus cn squared, where lambda is the wavelength and n is the line number. Let's see if this works. If we try to fit a polynomial to our measured wavelengths, we immediately run into problems. Even after fitting the polynomial to match the first line perfectly, the errors grow rapidly. By the fourth line, we're off by nearly 30 nanometers. This model clearly fails. Maybe the wavelengths are evenly spaced? Perhaps each line is separated by a constant amount from the previous one? Lambda sub n equals lambda sub 1 minus the quantity n minus 1 times d, where d is the spacing between lines. Let's calculate the actual spacings. From 656 to 486 is a difference of 170.2 nanometers. From 486 to 434 is 52.1 nanometers. From 434 to 410 is 23.8 nanometers. These spacings are clearly not constant. This model also fails. At this point, you might wonder if there's any mathematical pattern at all. The wavelengths seem almost random. In 1885, a Swiss schoolteacher named Johann Balmer made a remarkable discovery. Instead of looking at the wavelengths themselves, he examined the inverse wavelengths, or wave numbers. The wave number, denoted nu tilde, equals 1 over lambda. This quantity has units of inverse meters or inverse nanometers. Let's convert our wavelengths to wave numbers. Remember to use consistent units. Let's work in inverse meters. Here are our wavelengths converted to meters and then inverted. The first line gives 1.524 times 10 to the 6th inverse meters. The second gives 2.057 times 10 to the 6th, and so on. Now let's look at the differences between consecutive wave numbers. This is where the magic happens. The difference between the first and second wave number is 0.533 times 10 to the 6th. From second to third is 0.247 times 10 to the 6th. From third to fourth is 0.134 times 10 to the 6th. Now here's the key insight. Let's look at the ratios of these differences. Divide the first difference by the second difference. 0.533 divided by 0.247 gives approximately 2.16. This is very close to 12 ninths minus 12 sixteenths, which involves simple fractions. After much trial and error, Balmer discovered that all the visible hydrogen lines fit a remarkably simple formula. 1 over lambda equals r sub h times the quantity 1 over 2 squared minus 1 over n squared, where n equals 3, 4, 5, 6, and so on for the visible lines. R sub h is a constant called the Rydberg constant, equal to 1.097 times 10 to the 7th inverse meters. This constant is the same for all hydrogen lines. Let's check how well this formula matches our measured wavelengths. For the first visible line, n equals 3. 1 over lambda equals 1.097 times 10 to the 7th times the quantity 1/4 minus 1/9. This gives 1.524 times 10 to the 6th inverse meters. Taking the inverse gives lambda equals 656.3 nanometers. This matches our measurement perfectly. When you test this formula for n equals 4, 5, and 6, you get 486.1, 434.0, and 410.2 nanometers. Perfect agreement with experiment. Here's an exciting question. If this formula is correct, can we use it to predict spectral lines that haven't been observed yet? The answer is absolutely yes. What if we use different integers in place of the two? What if we use 1 squared in the formula? 1 over lambda equals r sub h times 1 over 1 squared minus 1 over n squared, where n equals 2, 3, 4, and so on. For n equals 2, this predicts a line at 121.6 nanometers. This is in the ultraviolet region, and it was indeed discovered later. This is called the Lyman alpha line. What if we use 3 squared instead of 2 squared in the denominator? 1 over lambda equals r sub h times 1 over 3 squared minus 1 over n squared, where n equals 4, 5, 6, and so on. For n equals 4, this predicts a line at 1875 nanometers, which is in the infrared. This line was also discovered and is called the Paschen alpha line. Scientists soon realized the pattern could be generalized even further. The complete formula involves two integers. 1 over lambda equals r sub h times the quantity 1 over n sub 1 squared minus 1 over n sub 2 squared, where n sub 2 must be greater than n sub 1 and both are positive integers. Different values of n sub 1 give different series of spectral lines. The Lyman series has n sub 1 equals 1. Balmer has n sub 1 equals 2. Paschen has n sub 1 equals 3, and so on. This formula is extraordinarily successful. It predicts every single spectral line of hydrogen with remarkable accuracy. But there's a deeper question. Why does this particular combination of integers work? What physical mechanism could possibly produce such a pattern? This puzzle led to one of the greatest breakthroughs in physics. In 1913, a young Danish physicist named Niels Bohr proposed a revolutionary model of the hydrogen atom that explained the Rydberg formula from first principles. Bohr made several radical assumptions that contradicted classical physics, but matched experimental reality. First, he proposed that electrons don't orbit at any arbitrary distance from the nucleus. Instead, they can only occupy certain special orbits with specific quantized energies. The electron can be in orbit n equals 1, or orbit n equals 2, or orbit n equals 3, but it cannot be anywhere in between. These allowed orbits are labeled by the integer n, called the principal quantum number. Second, Bohr derived that the energy of each allowed orbit depends on n squared in the denominator. E sub n equals negative 13.6 electron volts divided by n squared. The negative sign indicates that the electron is bound to the nucleus. For n equals 1, the energy is negative 13.6 electron volts. This is the ground state, the lowest energy state. For n equals 2, the energy is negative 3.4 electron volts, which is higher, less negative. As n approaches infinity, the energy approaches 0, which corresponds to the electron being completely free from the atom. Third, Bohr proposed that light is emitted when an electron jumps from a higher energy orbit to a lower energy orbit. The energy difference equals the photon energy. Delta E equals E sub n2 minus E sub n1 equals hf equals hc over lambda, where h is Planck's constant, f is the frequency, and c is the speed of light. Now let's see how Bohr's model leads directly to the Rydberg formula. This is where everything comes together beautifully. Delta E equals negative 13.6 over n sub 2 squared minus negative 13.6 over n sub 1 squared. This simplifies to 13.6 electron volts times the quantity 1 over n sub 1 squared minus 1 over n sub 2 squared. Since this energy equals hc over lambda, we have hc over lambda equals 13.6 electron volts times that same bracket. Solving for 1 over lambda, we get 1 over lambda equals 13.6 electron volts over hc times the quantity 1 over n sub 1 squared minus 1 over n sub 2 squared. When you calculate 13.6 electron volts divided by hc using the proper constants, you get 1.097 times 10 to the 7th inverse meters. which is exactly the Rydberg constant. The Rydberg formula emerges naturally from Bohr's atomic model. The empirical pattern we discovered has a physical explanation. When an electron jumps from orbit n equals 4 down to orbit n equals 2, it emits a photon whose wavelength is given by the Rydberg formula with n sub 1 equals 2 and n sub 2 equals 4. This produces the H-beta line at 486 nanometers. We now have a complete physical picture. The atom has quantized energy levels. Transitions between these levels produce photons. The wavelengths of these photons follow the Rydberg formula because of the 1 over n squared energy dependence. You might wonder, why does the energy depend on 1 over n squared specifically? This comes from solving Schrödinger's equation for the hydrogen atom, but Bohr derived it using quantization conditions. Bohr assumed that the angular momentum of the electron is quantized in units of h-bar, which is h divided by 2 pi. L equals nh bar equals nh over 2 pi, where n is a positive integer. This quantization condition, combined with classical mechanics, leads to the 1 over n squared energy formula. Bohr's model was spectacularly successful for hydrogen. It explained the Rydberg formula, predicted new spectral lines, and gave the correct value for the Rydberg constant from fundamental physics. For hydrogen, every single spectral line could be explained and predicted with perfect accuracy. However, the model failed when applied to atoms with more than one electron. It couldn't explain the spectra of helium or heavier elements. Bohr's model was eventually replaced by full quantum mechanics in the 1920s, which uses wave functions and the Schrödinger equation. But Bohr's insights about quantized energy levels remain central to our understanding. Let me summarize this remarkable scientific journey. First, careful experimental measurements revealed discrete spectral lines at specific wavelengths. Second, simple models like polynomials or evenly spaced wavelengths failed to match the data. Third, a pattern was discovered in the inverse wavelengths involving simple integer combinations. Fourth, the Rydberg formula emerged as an empirical fit that predicted all hydrogen lines with one universal constant. Fifth, Bohr constructed a revolutionary atomic model with quantized orbits that naturally produced the Rydberg formula. This journey transformed a numerical pattern into deep physical understanding. The integers in the Rydberg formula correspond to actual quantum states of the atom. This story illustrates the power of mathematical patterns in physics. When you find a simple mathematical relationship in nature, it's often a clue to deeper physical principles. The path from Balmer's empirical formula in 1885 to Bohr's quantum theory in 1913, and then to full quantum mechanics, shows how science progresses from observation to pattern recognition to theoretical understanding.